everyone, welcome back to my YouTube channel. This is chapter 3, classification of elements and periodicity in properties. Now let's begin our chapter with a simple question. Why do we need to classify elements? Imagine I write the names of 180 elements randomly. There are total 118 known elements. Right, there are total 118 known elements. Has its own different physical properties and chemical properties. Studying each one individually would be very difficult, right? And classification helps us group similar elements together, making them much easier to compare and understand. Okay. Another important advantage is that it allows scientists to predict the properties of unknown elements or newly discovered elements, right? So, classification provides a systematic way to study chemistry instead of memorizing every element separately. So, remember this one line, classification organizes elements in a systematic way, right? Systematic way, making them easier to study, compare and predict. This is the periodic table of the elements, right? So, this is the total 180 elements in the periodic table. So, there are groups and periods, right? This is the atomic number, this is the symbol, this is the name and this is the atomic mass. We will study later in this chapter. Next slide is characteristics of a good classification. Why do we classify elements at all? Imagine your school library. If all the books were mixed together without any order, would it be easy to find one book? No, right? Similarly, chemists also needed a proper system to arrange elements. A good classification should have these characteristics. Okay, so first, it should group similar elements together. For example, sodium and potassium. Okay, sodium and potassium should have a similar chemical property, so they are placed in the same group. Okay, second, it should separate dissimilar elements. Elements with a different properties, different chemical or physical properties should not be placed together. Third, it should predict new elements. A good classification should even help scientists discover elements that have not yet been found. Fourth is, it should explain periodicity. That means similar properties should repeat at regular interval. And the classification should be simple and systematic and logical so that everyone can understand and remember it easily. Okay. So remember this, a good classification doesn't just arrange elements, it helps us understand and even predict their behavior. Okay. Next slide is historical development of the periodic table. Now that we know why classification is important, let's see how scientists develop the periodic table over time. Finding the perfect way to arrange elements wasn't easy. Many scientists tried different methods and each one improved upon the previous one. Let's look at this journey. First, we have a Dobereiner Triads. Okay, so he grouped elements with similar properties into group of 3. Next is Newlands Law of Octaves. He observed that every 8 elements show similar properties, just like musical notes repeat every 8 notes. After that came Mendel's periodic table. This was a major breakthrough because Mendel's arranged elements according to their atomic masses predicted the existence of undiscovered elements, right? And finally, scientists developed the modern periodic table, okay, which is based on the atomic number and is the periodic table we use today. Okay, so think of it as a journey, that is Dobereiner Dobereiner, Newlands, Mendel's, and modern periodic table. Modern periodic. Next slide is Dobereiner Triads. Now let's learn about the first successful attempt to classify elements, that is Dobereiner Triads. This method was proposed in 1870 by the German scientist Johann Wolfgang Dobereiner. Okay, so Dobereiner observed that some elements with the similar chemical properties could be arranged in group of 3, and he called this group as a triads. But there was another interesting observation. He found that atomic masses of the middle element, is approximately equal to the average atomic masses of the first and the third elements. Okay, so let's understand with some examples. First, Dobereiner triads is lithium, sodium and potassium. Lithium has a atomic mass 7 and sodium 23 and atomic mass of potassium is 39. If we calculate the average of lithium and potassium, then what we got? We got 23, which is the atomic mass of sodium, right? So this triad follow the Dobereiner triads, right? Second triad is calcium, strontium and barium. Their atomic masses are 40, 88 and 137, right? The average of calcium and barium is approximately equal to 88, which is atomic mass of strontium, that is 88. Okay, again this rule works. Okay, third triad is chlorine, bromine and iodine. The atomic mass of chlorine, iodine and bromine is 35.5, 18 and 127. So the average of chlorine and iodine is approximately equal to 81, which is very close to 80, right? So the atomic mass of bromine. Okay, so 18 is the atomic mass of bromine. So this triad also satisfies the rule. We can conclude that from this example, we can conclude that elements in a triad have a similar chemical properties and the atomic mass of the middle element is approximately equal to the average of atomic masses of the other two elements. Okay, so remember one important limitation. Dobereiner triads work only for a few elements. So scientists needed a better classification system. Okay, so this is all about the Dobereiner triads. Now let's move to the second important attempt to classify elements, that is Newlands Law of Octaves. This classification was proposed by the scientist Newland in 1865. Newland arranged the element in increasing order of atomic masses. While studying this arrangement, he noticed an interesting pattern. He observed that every 8 elements had properties similar to the first element. This repeating pattern became known as a law of octaves, right? Let's understand this with simple table shown here. Okay, so if we start counting from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and sodium. Notice that sodium is the 8th element after the lithium, right? So both have a similar chemical properties. Similarly, if we start from beryllium, so magnesium is the 8th element, right? So they also show the similar chemical properties. So this repetition continues, which leads Newland to propose this law of octaves. Now you might wonder why it is called as a law of octaves. The answer comes from the music. Okay, so in music, 8th note is repetition of the first note. We have the notes, right? Sa, re, ga, ma, pa, dha, ni, sa. So the 8th note, that is sa, repeat the first note, right? Repeat the first note. Okay. In the same way, every 8 elements repeats the similar properties. That's why Newland compared the arrangement of element with the musical notes, right? So let's quickly summarize the feature, that is elements were arranged in the increasing atomic masses, right? Every 8 elements shows similar properties. He compared this repetition with the musical notes of octaves, and this law also had some limitation. It worked only up to calcium, right? Beyond calcium, the pattern no longer worked correctly. Also, some dissimilar elements were placed together, which created confusion. Another limitation was that noble gases had not yet been discovered, so they were not included in the arrangement. So remember the one line of Newlands Law of Octaves. Newlands arranged elements in increasing atomic masses, observed that every 8 element had similar properties, just like the 8th musical note repeats the first. In the next slide, we will study the Mendel's periodic table, which became one of the greatest milestone in the history of chemistry. Okay, so this is all about the Dobereiner Triads and the Newlands Law of Octaves. So we will learn Mendel's periodic table in the next classes. Until then, take care. Bye bye.